Hi, my name is Max Bolger, and I'm a computational data science major at Hamline. For the showcase, I'm going to talk a bit about my capstone project, which covered the WNBA. What I did is I used Streamlit, a open source Python web app development framework, to create a interactive UI that runs an in-depth analysis on any of the 990 players to ever attempt a field goal in WNBA history. It leverages results from a machine learning shot probability model that I made that uses 16 features to calculate predicted probabilities for the result of any given shot and turns it into an interactive UI. So this project was cut into basically three main parts. First, I had to do some data collection and web scraping. Secondly, I had to do machine learning model development. And lastly is what you see here, the UI. I'm going to cover mostly the UI here that I've created, and I'll briefly touch on the other two portions. So first, diving in here, we can select any player to have selected a shot in WNBA history. We'll go with Sue Bird. And we can select a range of years. We'll go 2013 to 2021. So we click run, and a few seconds here, a bunch of stuff will pop up. So first, we'll just start at the top. We have a player headshot and some stats about themselves, their age, their weight, position, etc. These were scraped from the WNBA Players API endpoint, and for some of the really obscure players that played in the late 90s and the beginning of the league, they actually don't have data in the WNBA API. So I had to create a second web scraper that scraped the Basketball Reference Players API endpoint. So that is how I got this data here. And over on the right here, we have some metrics. So first, we'll just start on the left here with field goal percentage. That is just the player's observed field goal percentage, the proportion of shots they make. Next here is three-point percentage. It's the same thing, just beyond the three-point line. And here we have FGOE, which stands for field goal percentage over expectation. So if we come over to the glossary here, we will see that FGOE is an additional measure of how well a player over or underperforms their expectation based on their shooting percentage. It is the difference between observed field goal percentage and the mean of their predicted make probabilities from my model. As we can see here, Sue Bird has an FGOE of 3.9, which means she is shooting 3.9% better than what our model expects based on its predicted probabilities. Next, we have PPS, which is just points per shot, an observed statistic, just the total points divided by total shots. So Sue Bird scores 1.04 points per shot, which is about a tenth of a point above league average. Then we have expected points per shot, which is, as we see over here, the expected points per shot given the model's predicted make probability multiplied by the proposed point value of a shot, which is 2 or 3. So as we can see here, a two-pointer with a make probability of 0.6 has 1.2 expected points, and a three-pointer with a make probability of 0.3 has 0.9 expected points tied to it. And we can get total expected points per shot by just dividing expected points rather than observed points by total shots. Then we just have PPSOE, which is points per shot over expectation, which is just the difference of these two, and it just shows how well a player is performing or overperforming or underperforming, based on my model's predicted probabilities. So here, Sue Bird is scoring 0.1 points per shot over what she is expected based on the model's predicted probabilities. So then we can come down here and we can see we have a shot chart. So I take every single player's XY locations for each shot in the time range and bin it into a hex bin. And from there, we can coordinate a color, blue meaning above league average and red meaning below league average, and the size relating to frequency in that shot location. So there's a lot of blue here. We can see that Sue Bird is a very good basketball player, so she's shooting above league average in pretty much most spots on the court. And we can also see that she does not shoot on the right side of the court that much. Well, let's see why. If we go over here, we can see Sue Bird's field goal percentage by zone. What this means is the court is divided into 6 different parts, and the bar represents the player's observed field goal percent in that zone. Then we have two lines. The dotted line is league average in that zone, and the solid line is that player's expectation in that zone. Another way to think of this is if we had infinitely many random WNBA players with the exact same shot profile as Sue Bird, that is to say, the exact same XY locations, the exact same shot types, everything, we would expect that average to converge at around 60%. So what this means is that Sue Bird is overperforming her expectation. We can think of this as FGOE, as we discussed earlier. We can think of that as FGOE for each spot on the court. So this means Sue Bird is providing something beyond what our model can comprehend, which most of the time is just inherent raw skill, because Sue Bird is one of the best players of all time. We can see that Sue Bird is performing above league average and her expectation for every position or zone on the court except the right corner 3, where she is well below league average and her expectation, and she's only taken 16 shots in almost the last 10 years. So this could be chalked up to some player awareness of Sue Bird, knowing she doesn't like that right corner, so she doesn't take shots there that often. This could be used for scouting reports if you're the opposition and you want to see what players are good and bad at. It can be used for, self-reflection as a player to see what you're good and bad at. A lot of good use applications. Over here, we have a career progression chart, which is just a rolling average by career games played over time. We have the player's field goal percent observed and their expectation compared to league average. We can see Sue Bird is performing well above her expectation and pretty much league average for most of her career as well. Just going to wrap things up here. So we'll do another player. We go to Diana Taurasi, who is another one of the WNBA greats. As we can see here, she is following what analytics is pushing in basketball these days, which is threes and layups. She's performing at or above league average in her expectation in most zones in the court. And she, on her rolling average, we can see that she actually had a dip. She was playing with injury and had a tough time recovering, but then she kind of bounced back, and then she's getting a bit old, so old age is probably at play here. But for most of her career, she was well above average. We'll do one more. We'll go to Simone Augustus. Hers is fun to look at because she defies analytics in basketball, actually. She only shot mid-rangers, but she was incredible at it. Definitely unanimous first ballot Hall of Famer when she's eligible. She's well above league average and her expectation, and as we can see down here, just destroying league average and her expectation throughout her entire career until the very, very end. So that is a little bit about my UI that I made that leverages my model's predicted probabilities. Just to wrap things up here, you can see all of the code that I used throughout this whole entire project, from scraping data, cleaning data, machine learning, modeling, benchmarking, and the app even. You can find all of that on my GitHub in my Capstone repo and my Streamlit app repo, which is just the code for the UI. But before I wrap things up here, I just want to cover the different part of my project here with the machine learning aspect. So here's an example of some model benchmarking I did when I was trying to choose the best model for this data. I ended up going with light GBM, or light gradient boosting machines, as it performed best on this data and was most calibrated. And what good calibration means is that for each bin, we want the mean predicted probability, or the proportion thereof, to be as close as possible to the actual observed fraction of positives. So on this line here, and it's a little bit messy, but we can see that some models are really bad, some models are closer to this straight line here. And then at the bottom, we can see we have some benchmarks. We can see training time, calibration score, ROC, AUC, and a bunch of others. And then I ran leave one season out cross-validation on these models and this data to get a more calibrated look at things, and we can see what that means here. Leave one season out cross-validation is a technique where every season is used as a holdout set. That is, for each of the 25 available seasons, we exclude one, train the model on the other 24, and then compare the model's predictions and the excluded holdout to what actually happened in that season. If the model is well calibrated, we would expect that, for example, 50% of shots with a make probability would be made 50% of the time. So that is pretty much all I have.